Hi, did you know that X-ray astronomy allows us to see the universe in a way that is invisible to the naked eye? X-rays reveal the most energetic phenomena in space. So join us on a journey to uncover the hidden secrets of the universe through the lens of X-ray astronomy. From black holes to neutron stars, X-rays allow us to peer into the most extreme and violent events in the cosmos. So without any further ado, let's begin. X-ray astronomy is one of the youngest fields in observational astronomy because X-rays do not penetrate the Earth's atmosphere. The history of X-ray astronomy is basically the history of high altitude and space astronomy. Early X-ray observations were done with sounding rockets and high altitude balloons. But the balloons did not rise above all the layers of the atmosphere, and in the X-ray part of the spectrum, even a little bit that was left mattered a lot. Sounding rockets are still being used for X-ray astronomy to study celestial objects emitting X-rays such as the Sun and supernovae. They offer a cost-effective way to carry instruments above the Earth's atmosphere, which absorbs most X-rays coming from the space. Sounding rockets are less expensive than satellites or orbital missions, making them a good option for testing new instruments or conducting short-duration experiments. These rockets travel on a parabolic trajectory, reaching an altitude of up to 1,500 kilometers before falling back to Earth. This provides a decent window of time, typically 5 to 20 minutes, for observations. One problem in observing X-rays is that it is very hard to make a mirror that works for these short wavelengths, which are less than 1 nanometer. That is because the typical spacing between atoms in a solid is about 0.1 nanometer, so the incoming radiation sees a rough surface with reflections of each atom producing a scattering in some random direction. But there is a way out. If we arrange the X-rays to come in at a very shallow angle of only 1 to 2 degrees with the surface, the atoms appear to be closer together and normal reflection can be achieved. This is called grazing incidence. But being constrained only by grazing angles makes it difficult to design a telescope that will collect and focus a reasonable amount of X-ray radiation. X-ray satellites are able to provide both continuous and spectral line observations. In the initial days, the spectral information came from detectors similar to those used by high-energy physicists, which are called proportional counters. In the past few decades, a number of X-ray satellites have opened our eyes to the X-ray sky. One of the earliest satellites used X-ray detectors which shared space with other experiments. Launched in the year 1970, Uhuru was the first satellite fully devoted to X-ray observations. It was also the first to survey the whole sky and compared to previous missions had very sensitive detectors. Uhuru found 339 objects, showing astronomers that many different types of objects radiate strong X-rays. Following Uhuru, which was a relatively small satellite, NASA launched a number of large satellites in their high-energy astronomy observatory program. The second in this series was the Einstein Observatory, which was the first to utilize the grazing incidence imaging and hence produced the first real X-ray images. Einstein's images changed the way we thought about many astronomical objects. It was almost like a blindfold had been removed. The next major turn achieved in the field of X-ray astronomy was with the sensitivity and angular resolution of the ROSAT satellite launched in the year 1990, followed by Chandra, which was launched in 1999. Both of these provided sub-arc-second imaging and grading spectrometry. Proportional counters were one of the early workhorses for X-ray astronomy. A proportional counter is essentially a sealed container with a window where X-rays can enter. Inside the container, there is a gas and electrodes. When an X-ray enters through the window, it ionizes the gas, producing a number of electrons and positively charged ions of the gas. This is where the electrodes play their part. They set up a strong electric field, and the electrons zoom across the gas chamber towards the positively charged electrodes, also known as anodes. If they are moving fast enough, the electrons will ionize other atoms of the gas on their quick trip across the detector, freeing even more electrons, which will then also zoom across the detector, ionizing even more gas atoms on the way, freeing even more electrons, which will ionize even more gas atoms. You get the idea. As a result, a huge number of electrons will reach the anodes. Their number depends on the gas used in the chamber and the energy of the incoming X-ray photons. This process turns the tiny interaction between X-rays and gas atoms into a relatively large signal at the anode. The number of electrons that reach the anode is proportional to the energy of the incoming X-ray. Recall that energy is another way of measuring the wavelength or frequency of light because E is equal to h times nu or hc by lambda, where h is the Planck's constant, c is the velocity of light, and nu and lambda are the frequency or wavelength of the light being measured respectively. This means that using a proportional counter, astronomers can find the spectrum of X-rays from an object in space. That is, they can find out how many photons at each energy are coming from that object. This also means that proportional counters can provide good energy resolution, allowing astronomers to distinguish between different types of X-ray energies. Some proportional counters are designed to be position sensitive as well, allowing them to determine the location of the X-ray source in the sky. Proportional counters are particularly effective for detecting soft X-rays, that is, X-rays with relatively lower energy. Better spectral resolution was obtained in proportional counters using a type of grating called a Bragg crystal. In this, the slits are the individual atoms in a solid. The Bragg's law states that when X-rays are incident on the surface of a crystal with an angle of incidence theta, they will reflect with the same angle of scattering. The waves from the crystal's surface can interfere constructively or destructively. Constructive interference occurs under the condition when the path difference is equal to the whole number n of the wavelength. The Bragg's equation can therefore be written as n lambda is equal to 2d sine theta, where n is an integer, lambda is the wavelength of the incident X-rays, d is the distance between the atomic layers, and theta is the angle with which the X-ray is incident on the crystal's surface. The law is dedicated to its discoverer Lawrence Bragg, a British-Australian physicist who shared the 1915 Nobel Prize with his father for this discovery. The Bragg's law describes the relationship between the wavelength of X-rays, the spacing of crystal planes, and the angle of reflection. The choice of crystal depends on the energy range of X-rays which are to be observed. Different crystals have different lattice spacings, allowing for the analysis of X-rays with varying wavelengths. When X-rays strike a crystal, they are diffracted at specific angles according to the Bragg's law. These diffracted X-rays are then caught by a detector, providing information about the energy distribution of the incoming radiation. The peaks corresponding to the constructive interference are called the Bragg's peaks. More recently, X-ray astronomers have been able to use solid-state detectors for X-ray observations, which give even better spectral resolution. By analyzing X-rays, astronomers can determine the wavelength and intensity of X-rays, which in turn provide valuable insights into the composition, temperature, and dynamics of astrophysical sources. For instance, around 30% of the total mass of a galaxy cluster is in the diffused gas found in between the galaxies. This gas has either been ejected from the galaxies therein or has fallen into the cluster. In either case, most of this gas is extremely hot at a temperature of around 10 million Kelvin and therefore radiates X-rays. In fact, combining X-ray data with others, especially at radio wavelengths, gives a complete picture of gas present in various systems. The huge bubbles created in the interstellar medium by the jets emerging from a central AGN in a cluster are magnificent examples of revealing the truth by using multi-wavelength data. Watch our video on multi-wavelength astronomy to learn more about this. X-ray emission is a key to understanding the history of formation of large-scale structures in the universe. Not just the wavelength, but even the morphology of the gas in galaxy clusters reveals interesting facts about them. For example, there is a direct correlation between the temperature of the gas and the total mass of the cluster. The gas in massive, dynamically relaxed clusters is hotter and more symmetrically shaped around the X-ray center relative to a newly forming galaxy cluster which is dynamically active. The latter may also show signs of subgroups merging with it via the morphology and temperature of the X-ray emitting gas, because in such a situation, the gas appears patchy and most of the times at relatively lower temperature compared to a relaxed, virialized cluster such as Coma. Next in line are the star-forming galaxies, which mostly emit soft, that is, low-energy X-rays due to the heating of the gas when stars are forming. However, a lot of these high-energy radiation are absorbed by the dust surrounding the star-forming regions and may contribute to the infrared instead of the high-energy end of the spectrum. The central supermassive black hole at the core of active galaxies emit X-rays due to the intense magnetic fields in the jets originating from them. Another example of X-ray emitting objects are supernova remnants. In a supernova remnant, various phenomena can lead to the emission of X-rays. The shock wave from the supernova remnants heats the surrounding gas, which can reach extremely high temperatures of tens of millions of degrees. This hot plasma then emits X-rays through thermal processes. High-energy electrons accelerated by the shock waves can also emit X-rays through synchrotron radiation. Synchrotron emission is particularly strong in regions with strong magnetic fields, for example, the narrow collimated jets from AGN. Last but not the least, the reverse shock which is formed when the high-pressure gas from the forward shock pushes back on the ejecta of the supernovae also contribute to X-ray emission. White dwarf stars are a source of X-rays as well. As discussed in one of our earlier videos, a white dwarf is a stellar core remnant mostly composed of electron degenerate matter. A white dwarf is very dense. Basically, in an Earth-sized volume, it packs a mass that is comparable to the Sun. While there is no nuclear fusion taking place in a white dwarf, it radiates light from its residual heat. Recall that a white dwarf which explodes into a type 1a supernovae is formed from low-mass stars. Prior to the explosion, the pressure in such a star is maintained by electron degeneracy pressure, which is a quantum mechanical phenomena. Such a star can be stable only if its mass does not exceed 1.44 solar masses, as discovered by the India-born astrophysicist Subrahmanyan Chandrasekhar, which is one of the reasons that NASA's X-ray satellite mission Chandra is named to honor him. Learn more about white dwarfs and degenerate pressure in our earlier video, a link to which is provided in the description below. In astronomy, cataclysmic variable stars or CVs are stars whose brightness increases irregularly by a large factor and then they drop back down to a dormant state. They were initially called novae, which literally means new in Latin, because the ones with an outburst become so bright that they are visible to the naked eye and remain invisible in the inactive state. CVs are binary stars that consist of two components, a white dwarf primary and a mass-transferring secondary. Both the stars are so close to each other that the gravity of the white dwarf distorts the secondary star and the white dwarf accretes matter from its companion. As a result, the secondary is often called a donor star and is usually less massive than the primary white dwarf. In most cases, the infalling matter, which is mainly hydrogen, forms an accretion disk around the white dwarf. Strong ultraviolet and X-ray emission is often detected from this accretion disk, powered by the loss of gravitational potential energy from the infalling material. The shortest currently observed orbit in a hydrogen-rich CV system is about 51 minutes. I hope you enjoyed this short discussion on X-ray astronomy and learned something new today. If you enjoy watching our videos, please share them with other astronomy enthusiasts and don't forget to like, share and subscribe to our channel. I will see you with another interesting topic in astronomy next week. Until then, take care.